We now have an understanding of how clock and data recovery works when you have the forwarded clock. That is, the clock that is used to generate data in the transmitter is also forwarded to the receiver side. Okay? So you have to adjust the phase. Now let's move on to clock and data recovery without the forward clock. Okay. So now, how would we go about doing this? One thing you have to realize is that you will have an oscillator, typically derived from a crystal oscillator, on the transmitter side. The crystal oscillator goes to some frequency multiplier, and you have some frequency of the transmitter. And then let's say on the receiver side, you have a physically different crystal. I mean, it has to be different because the receiver is far from the transmitter and you don't have the forwarded clock from the other side. And you have FRX. Now, it doesn't matter how close to each other they are. They could be within 10 parts per million or 1 part per million or even closer. It just doesn't work in that. You know that if you plot the phase of two signals of different frequencies, they'll look like that. Now, if the frequencies are very close, it means that the slopes will be close. But if you wait long enough time, the phases will diverge. Okay? So you can't operate the receiver with a clock that is independently set, independently of the transmitter. Okay? Because we are assuming these communication links which operate not for a short duration of time, but essentially they start and go on forever. Okay? So if you wait for a long enough time, if the frequencies are not exactly the same, they will drift. I mean, the phase will drift substantially. Okay? So this won't work. So essentially you also need to recover the transmit frequency in some way. Okay. Eventually, in whatever period you are receiving the symbols, there has to be as many rising edges in the receiver as many rising edges in the transmitter, right? The number of data symbols has to be the same. Otherwise, the communication is in error. Is this okay? So now, let's see. There are many ways to derive the topologies that are used for clock and data recovery without a forwarded clock. We have already done substantial amount of work understanding the clock and data recovery with forwarded clock. So we'll take that as starting point and then go from there. Okay. So again, I'll start with a linear phase detector because it's easy to understand and model. And I have a data input D and I have my usual delay line, control delay line, which moves the phase of the clock. Okay. So this is the CDR with forwarded clock, the one that we are all familiar with. Now, when we don't have a forwarded clock, essentially we need a clock generator in the receiver, right? We have to have something that generates this periodic clock. And of course, it should have a variable frequency because we don't know what the exact frequency is. We need to be able to vary it so that it gets adjusted to be the exact same as the transmit frequency, right? So what is such a block that you know, something that generates a variable frequency? a VCO, voltage controlled oscillator. So it's typically denoted by a symbol like this. It has some control voltage and it has a signal at the output of some shape. Okay. How do you model a VCO? So this is a voltage controlled oscillator. By the way, I will say voltage controlled oscillator, but what we need is an electronically controlled oscillator. It could be current controlled or voltage controlled, but it's common to say VCO regardless of the actual implementation. Okay. What is the output of VCO? The periodic, so basically, if the control voltage is a constant, the output will be periodic at some frequency, and if you change the control voltage to a different constant, it will be periodic at a different frequency and so on. Okay. The actual waveform can be anything. It can be a sine wave or a square wave or whatever. I will, as usual, model it as cos, but the waveform may not be a sinusoid. It could be a square wave or something in between. Okay. We have already seen while understanding phase that the waveform shape doesn't matter. It's you can take any other function which is periodic with 2 pi and you will have the same result. Okay. So the crucial thing is how this theta of t is related to V control. So what would be the model for that, you think? So it will be basically some 2 pi f naught t plus 2 pi integral kVCO V control dt. Okay. So this part is known as the free running part. That is, if you set V control to 0, it will still be oscillating at some frequency. Okay. And then the rest of it is the control part due to V control. Okay. So now if you look at the instantaneous frequency or omega, it will be 2 pi f naught plus kVCO times V control, or f, maybe I will call it omega I and fi, denoting instantaneous frequencies. So this last equation is probably what you would normally see. It has a frequency that is controlled by V control. Okay. And I have assumed a linear model where the frequency is a linear function of frequency varies in a straight line with V control. Okay. The most important thing is this theta, the phase, right? You shouldn't write it as 2 pi fi times t. This is not correct. Okay. So it is the integral of this. That means that if V control is varying, you will get the time integral of that. Okay. So it is not this times t. Is it okay? Any questions? So clearly you can see that if you, this f naught or omega naught, f naught is known as the free running frequency. Basically, if you take a real VCO and you plot its Fi versus V control, okay, what you get will be some curve like this. Okay, it will actually be non-linear and so on. As usual, you have some operating point around it, you can linearize this. Okay, so if you do that around that point, this will be the free running frequency and the slope will be kVCO. Okay. By our definition, the units of kVCO will be hertz per volt, because we have made the instantaneous cyclic frequency to be kVco times V control. Again, this definition can vary. Sometimes this 2 pi is absorbed into kVco and the instantaneous radian frequency is made proportional to V control with a constant. It's all the same, but there will be some scaling of 2 pi, etc., or 1 by 2 pi. Is this okay? So this is the model of a VCO. A voltage controlled oscillator is something whose instantaneous frequency can be controlled using a control voltage. It's very common for the sake of modeling to assume that the instantaneous frequency versus control voltage has a constant slope, right? It's a straight line. In reality, it will be some nonlinear stuff. And the instantaneous phase of the voltage controlled oscillator will be the integral of this. Okay? Is this okay? And in fact, this integral relationship is exploited in some applications in the last few years to realize an integrator, because the phase is an integral of this. That is exploited. In fact, those of you who attended the seminars on Saturday, the very first talk, VCO was used as an integrator. Okay? So it can be used, but that's not our interest right now. We just want to use it to clock our clock and data recovery circuit. Okay? Now let's see how to use it in this. So let me make 2 copies of this. Now this is with forwarded clock. Okay, whereas this one, let's say, is without forwarded clock, and obviously I don't have this and I can't use whatever I had earlier because I don't have any clock from the other side. I assume that basically I have my VCO. It has a certain free running frequency F0, and this is it has some control voltage, and this is what I use to clock my data. Okay, and I will need a phase detector anyway, because eventually I have to find the phase difference between clock and data, so I will keep the phase detector here. Okay. Now first I will assume something completely unreasonable. That is that the free running frequency here is exactly same as the transmit clock frequency. Okay. This is of course not practical, so later we will fix this, but first assume that the free running frequency is exactly same as the transmit clock frequency. Okay. So now again we have sort of reduced it to earlier case where we know the frequency and we have to adjust the phase. Of course, now the clock is coming from a voltage controlled oscillator. Earlier the transmit clock was delayed using a delay line. Now we don't have a transmit clock, so we can't use that. We have to generate the clock here and adjust its phase. Okay. So the next thing is, how should we generate this control voltage? Okay. So now let me look at the system I have here. I know that this works, right? This is the case with the forwarded clock works. Okay. So now again, like I said, there are many ways to try and derive the case without the forwarded clock. I will try to mimic whatever we have working, right? So I know that this works, and this artificial case with the free running frequency being exactly equal to the transmit frequency, I will try to make this work in exactly the same way as this one. Okay. Now what do I mean by that? What I mean is that the relationship between this data and clock should change in the same way as in this circuit. Is this okay? So to do that, let me introduce a small modification here. I have my input clock. I will put it through a control delay line and this is what was used to clock the data, right? The control delay line was clocked using V control. Okay. So now let me do this. Let's say it has locked initially. Okay. Okay. So then I will have some phase for this clock. Now imagine I do this experiment. I will look at what clock is being generated, the waveform, its timing, and I will break this connection and instantly connect it to a source which generates a clock of the same phase. You understand? So this would have locked with the rising edge of clock in the middle of data. So I let it lock, and then I make a voltage source which has the same timing as the recovered clock, and I instantly swap this feedback derived clock from my independent clock. Is this okay? Is it clear what I have done here? No? Okay. So what I did was, this one will recover the clock, you agree? So the data is like this. This clock would have been that way. Okay. So now I will make a clock source which generates this exact waveform with its rising edge in the middle of data. Okay. And I instantly swap this feedback derived connection with this. Okay. So do you agree that this clock will still be in the middle of the data? What will be the average output of the charge pump? 0. Okay. So the control voltage won't move, and let me call this clock prime. How will clock prime be related to clock? It will be the same. Okay. That's how I derived it, right? It will be exactly the same. Okay. So now let's say I introduce a phase step in the data. Okay. That is, I advance all the data edges to the left by a certain amount starting from that point after I replace this. Okay. So what do you think will happen to this phase of this clock prime? So at some point, let's say, I mean that's my definition of t equal to 0, I introduce a step in the phase of the data. What will happen to phase of clock prime? It will, yeah, basically what happens is I introduce a phase step in this. This phase has not changed. If data is leading the clock, what happens? You will have an average positive output from the charge pump. So that means that you will have a current in this direction. This V control will ramp. It won't ramp like that. It will have this jagged nature, but on average it will keep ramping up. Okay. So what happens to this phase of clock prime? It will also keep ramping up, right? If I plot phase of clock prime minus phase of the clock, initially they were aligned, and once I introduce the phase step in the data, it keeps ramping up. Okay. So this is the familiar, basically, if you have a step here, this will, the feedback signal will be the integral of that. So when you close the loop, essentially this will get aligned and the phase becomes equal to 0. Okay. Is this clear? So what I did was I take the system I already have, the clock and data recovery system with the forwarded clock. Then I break the loop and introduce a step in the phase of the data. Okay. Then I look at what the feedback looks like. I mean, you would have done this a lot of times with op amps and so on. There, of course, you are simply looking at the feedback signal. Here I am looking at the phase of the feedback signal. That's all. That's what is relevant here. Okay. The phase will be a ramp. Right. So now what I do is, in this system, right, I try to do exactly the same thing. Okay. So let me again, I break this and I clock this with an independent source which is aligned to the data correctly. Okay. So the data is like this, the clock is like that. This is an independent source. Okay. Now this is clock prime that is coming from the VCO. Okay. Now what I want is, if I introduce a phase step in the data, right, the phase of clock prime minus clock should ramp up with time. Is this okay? So this will then mimic exactly what I had in the other case. Is it okay? So again, lots of ways to derive this, but I am choosing this one. Do it from the analogy. I want theta ck prime minus theta ck to increase with time once I introduce the phase step. Okay. So then the question is, how do I close this loop, right? So what happens if I introduce a phase shift in the data? I mean a phase step in the data. Let's say all edges are moved to the left. What will be this current? What will be the average current? It will be greater than 0. The average current will be greater than 0. So now I have to somehow take this current and generate a V control which gives me this ramping phase. Okay. Is this clear? So what kind of V control will give me a phase ramp? In a VCO, what should be the control voltage? So if the control voltage was 0, it would have been oscillating at the free running frequency, which I said is the same as the transmit data frequency, right? Now, what kind of V control, what waveform of V control should I have so that the phase of the VCO is a ramp? Constant, obviously, because the phase of the VCO is the integral of the control voltage. So for the phase of the VCO to be a ramp, the control voltage should be a constant, right? And then here, if I introduce a phase step in the data, that is, there is a constant phase shift between data and clock, this ICP will be some constant current. ICP meaning the average value will be some constant. So how do I derive this V control from this current? What's that? How do I get a constant current from a constant voltage? Oh, sorry, constant voltage from a constant current. Pass it through a resistor. That's all. So all I need to do is okay. This will work in exactly the same way as the other one, right? Meaning now if there is a constant phase shift between data and clock, there is a constant average current flowing out of this which gives a constant voltage here and which causes this phase to be a ramp. So now if I close this loop, the behavior will also be exactly same as the one with the forwarded clock. Is this okay? The only thing is, of course, I have assumed a completely artificial constraint that the free running frequency of this is the same as the transmit frequency. Okay. So when will this reach steady state? Okay. So then what happens? What will be the control voltage value? 0. The control voltage value will be 0. The output frequency will be F0, which is the same as FTX. And the phase would have aligned itself such that this clock is in the middle of data. Okay. No phase correction is required. Is this fine? Any questions? Okay. Now of course, this F0 is not the same as FTX. Okay. So let's say this FTX is slightly more than F0. Okay. What happens in this case? What do you think will happen? Huh? No, if the frequency keeps on varying, the whole thing is not functional at all. So if the transmit frequency is slightly more than the free running frequency, How will this reach steady state? What is small negative? Why should it be negative? First of all, what is the absolute necessary condition to have steady state here? The frequencies should be the same, right? Otherwise, I mean, the two things are slipping past each other. There is no steady state. The frequency output of the VCO should be the same as the transmit frequency, right? Then you will have one rising edge in every data symbol. Where it is, we will see. But there will be one rising edge in every data symbol and it can reach steady state. Okay? But now, given that the transmit frequency is more than the free running frequency, what kind of control voltage will we need for this to happen? We need to have some small positive control voltage. And for this to happen, what should be the relationship between data and clock? Data should be? Yeah, so basically clock should be lagging the data, right? Clock cannot be aligned to the data, but clock should be lagging the data. Is this okay? So we came up with something with a VCO, so we don't need the forwarded clock anymore. That part is fine. And if the free running frequency of the VCO happens to be exactly same as the transmit frequency, then the clock will get aligned to the middle of the data. I mean, clock will be aligned to the data as required. Now, of course, since we cannot enforce this condition at all, let's assume that ftx is slightly greater than f0. The only way to reach steady state here meaning to have one edge of the VCO in every cycle of the data, you should have a control voltage that is positive. And to produce that control voltage, you need phase offset between data and clock. Is this clear? Yes or no? Okay. So now, of course, this is a serious problem because the more it deviates from f0, okay, the more phase offset you require, and beyond some point it doesn't work at all, because the whole idea is that you should be aligned to the middle. Maybe a little bit to the left is okay, but if you keep going to the left or the right, at some point the bit error rate increases. Okay, so this won't work at all. So we have to fix that. Is this okay? So now the state is that it works for when the free running frequency equals the transmit frequency, but of course that's a very artificial condition. So effectively we don't have something that works. So how do we get this to work? The hint is that we do know one particular case where it does work, right? Where the free running frequency is equal to the transmit frequency. So now the next question is, if I give you I have a VCO and it has a certain free running frequency f0. Okay. Now, using this and some simple modification, can you give me a VCO with a different free running frequency? I mean, can you put this in a box with maybe some other components? What's that? Yeah, basically it's actually trivial. So in that, if I have some V control and some V offset here, I add it and supply it to the VCO, and this has a free running frequency of f0. Okay. So if I write the instantaneous frequency here, it will be f0 plus kVCO times V control plus V offset. But the external control voltage that I apply to the box is just this, right? So I can write this as f0 plus kVCO V control plus kVCO times V offset. Okay. So now, sorry, let me write V offset here and V control there. So as far as if I plot now this Fi versus this external V control, I'll have something like this, where this part will be this whole thing, right? So now the free running frequency is effectively changed. Okay? Is this clear? The free running frequency is not some sacred number. If I add a DC offset, it will change. Okay? So now somehow the trick is that I have to add a DC offset and I have to keep on varying it until my new free running frequency becomes exactly equal to the frequency of the transmit data. Is this okay? So this by itself works only when the free running frequency matches the transmit frequency. So what I will do is, my new introduction is that I'll add V offset and I keep on varying it until the free running frequency becomes exactly equal to the transmit frequency. Okay? Now how will I do this? This, of course, I need to come up with a circuit arrangement to accomplish this, right? So how do I even know when the free running frequency matches the transmit frequency? What indication do I have? Or how do I know that it is the free running frequency is not equal to the transmit frequency? What's that? V control will not be 0. So what should I measure actually? That is correct. So if I have to look at either essentially, if the free running frequency doesn't match the transmit frequency, it will lock with some phase offset, right? So I can look at this phase offset, or equivalently I can look at the average charge from current or this voltage. All of them equivalently have the same information, right? So if F0 is not equal to Ftx, then this will not be 0, or the average ICP will not be 0, or the average V control will not be 0, and so on. Okay? Is this okay? So then what do I do? So essentially what I should do is, I have to continuously vary V offset until I can look at any of these quantities until they become equal to 0, right? So essentially I need so if I need this kind of control, right, I have to observe some quantity, some measure of error, and based on that I have to control something. That is, I have to continuously adjust this quantity until this error becomes 0. So the block that will help us do that is an integrator, right? The integrator has to be driven by this error. Any of them is fine. They are all the equivalent, I mean, they are all just proportionally related to each other. So I can take any of these things, integrate that, and add this offset. Okay? So this should come from an integrator, and the input to the integrator can be any of these 3. Okay? Right? And you can choose to integrate that in any which way you want. So now what will happen? This, if the phase difference is not 0, then this output of the integrator will be either constantly ramping up or ramping down. It will keep on adjusting V offset. And this V offset will move and it will lock to a new phase offset and so on. And then the whole thing will settle down only when the integrator output is constant, which means the integrator input is 0, which means that the phase offset here is 0. Okay? Now one thing you have to observe in this whole description, I assume that when does what is the phase offset between these two? That is the steady state phase offset, right? So let's say let's say I don't have this integrator, I just have some V offset, okay? And the free running frequency is now, the effective free running frequency is different from the transmit frequency. it will settle to a phase offset. Basically, the steady state phase offset is what is not 0. Okay. So now, essentially what you have to do is, effectively, you have to set a particular value of V offset. You have to let this settle to steady state, look at the phase difference. If that is not 0, you try a different value of phase offset and so on. So what it means is that you have to let this original loop reach steady state before you change it, before you change the value of V offset. In other words, essentially this path here, this integration should be very slow compared to, it should be so slow that this other loop reaches steady state before you see any appreciable change in V offset. Is this okay? Any questions here? Now, how do I implement this? How do I implement? Okay, first of all, I have these three quantities here. You can integrate any of them. Which is the easiest to integrate? Voltage? ICP, right? How do you integrate ICP? So if I pass ICP through a capacitor, okay, across that I will get the integral of okay. So now I also said this integration has to be very slow. That is, this is the offset that you want, right? This is the offset that you want to apply to the VCO. I said that this offset should change very slowly so that before you see any appreciable change, the other loop should reach steady state. So what does that mean? Should use a large capacitor. Okay, we'll later see how large is large, but you expect that this has to be a large capacitor. Okay. So essentially what I want is, I want the integral of this I control, this ICP to be added to this V control. And what is this V control? V control is just, what is it? ICP times R. So I have to add ICP times R to 1 by C integral ICP dt. Okay. So how should I do this? So all I need is basically the same current, the current flowing through the resistor is giving you the original V control, and current flowing through the capacitor is giving you the V offset, and what you apply to the VCO is the sum of the two. Okay. So you generate that directly by okay. Is this okay? And for now I will say this C has to be large. Okay. So that means that if you go from, if you sort of look at cycle to cycle, there is very little change in the voltage across the capacitor. It acts like the offset. Okay. But the frequencies were different. If frequencies are different, what happens is that slowly there will be charge accumulated on the capacitor, and eventually the voltage across the capacitor should be such that the voltage shift will cause the appropriate frequency shift. Okay. So essentially I will call this VC from here on, it's the voltage across the capacitor. The role of VC is to move the VCO frequency to the right value. Okay. And the role of VR is to provide instantaneous phase corrections. Okay, if the data phase changes instantly, like it can be moving rapidly back and forth, that change will be provided by VR, because within one cycle the voltage change in VC will be very small. Okay, but if the frequencies were different, then there is a systematic change in the phase, right? It will go on accumulating. So it will go on accumulating charge on VC or the voltage across VC, and eventually this will become a constant, and the constant will be such that with that voltage, VCO is operating at the right frequency. Okay. So this circuit now recovers both the frequency and phase of the data. Is this okay? So the way I did it was by, first of course I needed a VCO because I have no source of the clock, and I needed an adjustable frequency. But first I assumed the same, the pre-running frequency is the same as that of the data frequency, so there is no frequency correction required. In that case, if I had only the resistor, it would work. It would work in the same way as the other system would work, the one with the forwarded clock. Okay. But now, because the frequencies will be different, I need to add an offset voltage to the VCO, and to get that offset voltage, essentially I have to integrate the phase difference. So I take the output of the same phase detector and pass it through a capacitor to integrate it. Okay. So this is a standard analog clock and data recovery circuit which is widely used. If you do it in an analog way, this is what you will use. Okay. So this is essentially you have two, sometimes this is called two paths. This kind of term you would have heard in control systems also. This is the integral path and this is the proportional path. So what do you remember about these things? This integral controllers and proportional controllers and so on. So one will have zero error with a step input, the other will have zero error with a ramp input and so on. Okay. So if you just had the proportional path, if you have a phase step, that will be tracked perfectly. That is, the loop will initially of course be in error, but eventually the clock will track the phase step. But if you have a phase ramp which is equivalent to the data having different frequency from the clock, that won't be tracked if you did not have the capacitor. But if you have the capacitor, even that will be tracked. That is, let's say you start off with different frequencies, that's like having a ramp error in the phase, but that will also eventually get tracked. Is it okay? So the next thing is, I mean, we have the topology. Now we have to again analyze, because right now everything we said is in a qualitative sense. I said I put a resistor, I didn't say how much. Similarly, I said a large capacitor, but how large is large? All this is, all this will come out of the analysis. Okay. Any questions on the derivation of this? And again, I don't show it. I essentially am drawing the clock recovery part, but the same phase detector also gives the data output, right? Because it will have some flip-flop which will have this as the D input, this as the clock input, and the output of that is the recovered data. After the clock phase is recovered, that's what is going to happen. Okay. Okay. Any questions on any of this? Yeah. So this, I mean, for these things to work in practice, right, you have to start from a frequency that is near the data. Okay. That is, you can't start from, let's say, a factor of 2 off. This is not going to bring it back to the right place. So there will be other auxiliary mechanisms which will bring the VCO pretty close to the data frequency. But then this will recover the phase, and then also will take care of all the dynamic variations. Over time it will change, and over temperature things will change. Even if the incoming data frequency is not changing, over temperature the free running frequency of the VCO itself can change. So it will compensate for all that. So the scenario that you are describing, where the data frequency was half, right, that cannot be dealt with this system. Okay. Because then, I mean, essentially, let's say you lock this to 10 gigabits per second data and then instantly change the data to 5 gigabits per second. That is essentially your repeating bits. It will stay locked, right? Meaning, let's say at 10 gigabits per second, the clock was in the center of the data. That means that this will give you like a zero average output. Okay. Then you are transmitting like this. But then at 10 gigabits per second, you start repeating every bit twice. Okay, every 1 or every 0, you repeat it twice. It's actually 5 gigabits per second data. But what will happen to the clock? It won't move at all, because Every time there is a transition, this is showing only zero phase error, right? It won't change. So it won't recover the frequency of the data in that case. It cannot. There is no information to do that. Okay. So in practice, actually, you bring this very close to the actual frequency. Meaning, for instance, you have a crystal in the transmitter and the receiver. Those two will be close enough, maybe within 100 parts per million of each other. And from there, you can take it and recover the frequency. Now, there are some situations where you have to recover the frequency also from a data, and the frequency can be widely varying. For that, you will need something else, like some other block which is known as a frequency detector, which is used to bring the VCO to fairly close to the transmit frequency. I mean, this circuit by itself cannot do it. Okay. Any other questions? So, what will be the phase model of this? So, essentially now we have as before, to create the model, we assume a certain operating point, which is that it is locked, and then look for deviations, right? So now at the operating point, let's say I'll call this theta d and it is theta ck, and then you have some V control. Okay. Now this theta d and theta ck are such that, I mean, by definition, this clock edges will be in the middle of the data. Okay. So let's say I introduce some data jitter or some increment in the data phase. What will happen? You expect that there will be some increment in the control voltage, and there will be some increment in the clock phase. Okay. So now we will make a model that will relate these increments. Okay. So what model will that be? So for this part, we have already done the work, right? We know that with input phase increments, what will be the average output current? I mean, I can also include, let's say, the average output current in the operating point would have been 0, and then when you add this increment, it will become plus some lowercase ICP. Okay. So this phase detector plus charge pump, we already know the model, right? We used it for the other case. And what will be the model for R and C? The incremental model for R and C. The same thing. I mean, it's basically the linear this one. The relationship between ICP and V control is given by the impedance of R and C. What will be the phase model of VCO? That's something that we have to see. So if the input has an increment of V control, what will be the increment in the output phase? Okay. And with that, we can complete the feedback loop, get the model, and get all the basically quantities relevant to the clock recovery. Is this okay? So please try to find the model of the VCO, the incremental model of the VCO, and then we can use that in the clock and data recovery circuit. Okay.